Hello, everyone. Let us discuss some problems of GATE 2020 physics exam. Okay, so this is a question from classical mechanics. It says a particle is moving in central potential v naught e to power minus r square. It has some angular momentum. Now, question is r1, r2 are stable and unstable point. Then some options are given related to it. Okay. So we know that if there is a question related to central potential and we have to find a stable, unstable point, then we first of all define the effective potential. So we write effective potential. V effective is equal to V of R. It is written like this, or plus some L square upon 2m R square. All right. So here effective potential is minus V naught and e to the power minus R square and plus this is L square upon 2m R square. So that's the effective potential. Now, if you plot this potential, okay, we can plot it easily. See, if you put r tending to 0, this term will dominate. Okay, and if you put r tending to infinity, so this term will become 0 and this term will also become 0. So ultimately both will become 0. Okay, but somewhere see L is actually given to be L is given to be some V naught. See, this is 1 by 2 root under V naught. So if you put the value of L, it comes out to be 1 by 8 actually here. So you can check that. Okay, so if you plot potential, it looks something like this. Okay, V effective versus R. So if we plot it, it will be something like this. Okay, I think it will be something like this. So this point is this is V effective versus R. So this point is basically corresponds to minimum value of effective potential, and this point corresponds to maximum value of effective potential. This will be called R1 and this as R2. Okay, so this corresponds to stable. Okay, this is stable. This R1 corresponds to stable point, and this corresponds to unstable point. Unstable point. Okay, so clearly we have one stable point and one unstable point. Okay, these actually correspond to circular orbits. Okay, particle will be moving in circular orbit of radius r1 and radius r2, which will be called stable circular orbit and unstable circular orbit. Okay, and you can see here r1 is at smaller value, so obviously r1 is less than r2. So this was one option given. Okay, and there is one, so we can tick. It was perhaps MSQ question, so one option, this option is correct, and there is one stable point and one unstable point. Okay, so these were also the options, so maybe 3 options will be correct here. Okay, all right, so now let's move to, so that's the simplest solution, okay, of this question. Now let's move to another question. This is question number 2. It says relation between Helmholtz free energy and internal energy. Okay, we know that see, Helmholtz free energy F is equal to U minus Ts. Okay, and we know that dF or S is defined like this. Okay, S is equal to minus del F by del T. This is at constant volume. Okay, this is how we define. Okay, so we can put value of S here. So F will become equal to U minus U plus, it will become U plus T and del F by del T at constant volume. Okay, so we have to find U. So U will be equal to F minus T and del F by del T at constant volume. Now, so this is the relation between internal energy and Helmholtz free energy, but this option was not given. So we can reduce this relation to the given options. Okay, so what we can do is see, we can write it like this. See, if you differentiate this term F by T, okay, with respect to T, okay, if you differentiate this, then what you actually get is see, here I'm just asking you to differentiate it. See, if you differentiate it, you get this term dF by dt, but you get here 1 by T term. Okay, but what you want actually is multiplied by T. Okay, and with a negative sign. So if you differentiate this term, okay, you get 1 by T with positive sign. So let's multiply here by T square. Okay, now you check. See, if you differentiate T, you get minus 1 by T square. So minus 1 by T square and T square cancel out. So you will get F here. Okay, so this if you differentiate this relation, you'll get back this one. Okay, so U will be equal to this much actually. Okay, so that's the relation between U and F. All right. So this was the second another question from GATE 2022 exam. Okay. Now let's move to another one more question. So this is a question from classical mechanics. Okay. Previous one was obviously from thermodynamics. Okay. So here it says if FQP and GQP are constant of motion, okay, and H be the Hamiltonian, then which of the following is always zero? इसमें बताना है ये Poisson bracket है, ठीक है? These are all Poisson brackets. So which of these are always zero? That is the question. Okay. See, these two are actually constant of motion. Okay, but see, these constant of motion are not depending on time explicitly. Okay, इसमें time dependence नहीं है, explicit time dependence नहीं है. There is implicit time dependence obviously. So we can say that if these are constant of motion and these do not depend on time explicitly, so therefore we must have a Poisson bracket of Hamiltonian with F equal to 0 and Poisson bracket of Hamiltonian with G also equal to 0. So we have these two situations. Okay, we can use these things when a given quantity does not depend on time explicitly. All right. So now so this thing we have now another thing, according to there is something called Poisson theorem, okay, which says that if there are two constant of motion and you calculate F and G, you may end up getting another constant of motion. So this will also be a constant. Is that okay? So this will also be constant. Okay, so if you calculate Poisson bracket of F and G, you may get another constant of motion. All right. So now we have these things. Okay, so now let's check options one by one. So if you check first option, see it is H plus F comma G. Okay, so it gives you, first option gives you H comma F or plus, okay, here F comma G. All right, so you see here H comma F is 0. So this is 0 plus F comma G is actually a constant. So this is not always 0. ये 0 नहीं भी हो सकता है, ठीक है? It may not be 0. So this is not always 0. Okay. Now second option, if you check, okay, you get here, see, you get here F H comma G and plus, okay, you get H comma G, sorry, H comma F and here G. That's what you get. All right. So that's what you get from here using the properties of Poisson bracket. Okay. So now you see this is 0 and this is also 0. So this actually gives you 0. So this is always 0. This is always. Okay, now C option, if you check, okay, C option, this is a Poisson bracket of F and G. As I said, according to Poisson theorem, constant of motion, two constant of motion has a Poisson bracket which gives you another constant of motion. So this is constant. So now it is a constant and it will obviously be independent of time actually, because F and G do not depend on time explicitly. So this is also independent of time. Okay, so now we know that if something does not depend on time explicitly, its Poisson bracket with Hamiltonian has to be 0. So therefore this is always 0. So C is always 0. C is 0 always. Okay, now D option, see, it says you can open it like this. It is H comma F and plus this is H comma G. And we know that both of these are, see, both of these are actually 0. This is 0, this is 0. So therefore this is 0 plus this is 0. So therefore it is 0 and this will be always. Okay, this is always 0. All right. So therefore here always 0 we are getting in three options. Okay, option B, C and D. All right. So that was the solution of this third question. Okay, now this is the fourth question. It says a charged particle Q oscillates with frequency omega. This was, I think, a simple harmonic motion actually. Okay, so with amplitude A, how power radiated depends on Q, omega, and W. Okay, see, this is the case of oscillating charged particle. So therefore, power radiated is given by Larmor formula, which is written as Q square A square upon, okay, upon this is Q square A square of 6 pi epsilon naught C cube. Okay, where A is acceleration. See, in case of SCM, we write displacement as x equal to A sine omega t. So therefore, acceleration is x double dot. Okay, so you get acceleration. Acceleration is equal to minus A. You get here minus A, and here you get omega square and sine omega t. Yeah, so, sorry, sine omega t. Now that's the acceleration. Okay, if you differentiate it twice. Okay, so this is the acceleration. Now we'll put it here. Since it is time dependent, we'll take its average. Okay, so if you calculate average power, we get here Q square and you put the value of a, you get a square omega square, and you get here sine square omega t. Okay, and here 6 pi epsilon naught and c cube. So average of sine square is 1 by 2 actually. For okay, so this gives you q square a square and omega power 4 actually here. See, there was omega square, you are taking square of acceleration, so you get omega power 4 here. So omega power 4 divided by 12 pi epsilon naught and c cube. Okay, that's the answer. Okay, so here q depends, so we can say that power radiated is proportional to q square a square omega power 4. So that was one option actually. Okay, now another question, it says Lagrangian system is this, okay, and this is a constant of motion, so we have to find the value of alpha. This is a constant of motion, so its total time derivative has to be 0. You write x dot plus y dot plus alpha x y is equal to 0. This is the basic general definition of constant of motion. If something is constant of motion, its total time derivative with respect to time has to be 0. Okay, so let's differentiate it. It gives you x double dot y dot or plus y dot and y double dot and x dot or plus alpha x dot and y or plus um, x y dot, that is equal to 0. So we have differentiated with respect to time. Okay. Now, to get the value of alpha, we need to put the value of these x dot, x double dot, y dot, double dot, x dot, y dot, etc. Okay. So for that, we need equation of motion. So we'll write x equation of motion. Okay. So you'll have to write equation of motion for x coordinate actually. Okay. So if you do that, we write equation of motion like this: d dt of del L by del x dot and minus del L by del x is equal to 0. That's the equation of motion. So if you differentiate this here, you get mx double dot, okay, and plus kx is equal to 0. So you get here x double dot is equal to minus k by m and x. Similarly, from y equation of motion, you get actually y double dot is equal to minus k by m and y. Okay, that's what you get. So let's put those things here. So see, you are getting k by m factor in both, so you will get here minus k by m common here. And when you put x double dot, see, when you put x double dot, you get here x y dot, and when you put y double dot, you get here y x dot, and plus alpha x dot y plus x y dot is equal to 0. Okay, so that's what we have. See, this x y dot y x double dot, this we can take common. Okay, so we get from here alpha is equal to, or you can just say that we are dividing by this. Okay, so this will cancel out. So you will get alpha minus k by m equal to 0. So therefore alpha is equal to k by m. So that's the answer. Okay, so this alpha was to be calculated. So this is the value of alpha actually here. Okay, now move to another question. Okay, where is that? So let's move to, it says 1/4 of a surface of a sphere is at potential phi naught, another 1/4 at 2 phi naught, and half at 4 phi naught. Okay, so calculate potential at center. So there is a mean value theorem, okay, in EMT, which says that suppose if there is a closed boundary, it is not, it is applicable for other kind of boundaries also, okay, not just for a sphere. It says that if there is a closed boundary and there is no charge inside it, okay, then potential at center is just the average of the boundary potential. Okay, so potential at center is equal to average of v at boundary. That is the mean value theorem. Okay, so we'll take average of this. Okay, so here potential is phi naught. So let's take average on area. Okay, so we'll multiply by area. So area is 1/4. Okay, then potential is 2 phi naught over area 1/4, and then potential is 4 phi naught over half of the area. Okay, and let's divide by total area. So that's the average taken over area. Okay, so a will cancel out. You will get here. So what you get here is phi naught will be common, and you can see here this is 3 and this is 4 phi naught actually. So when you add it, okay, you will get, I think, 11 phi naught by 4. Okay, that's what you get. Yeah, so that's the answer. Potential at center will be equal to this much. Okay, so this was an application of mean value theorem in electrostatics. Okay, now let's move to another question. See, it says this is the Hamiltonian for LS coupling, spin orbit coupling. This is actually, so you have to calculate energy difference between these two levels. Okay, so let's write. See, energy in this case is actually written as VSO divided by 2, and this is J into J plus 1 and minus L into L plus 1 and minus S into S plus 1. Okay. Now here for these two states, actually J is different, but L is 1 and S is not specified. So S we take to be same actually. Okay. So only J is different. So this term will actually be subtracted. Okay. So if you write energy for suppose J equal to 1, okay, sorry, half, and minus energy for J equal to 3 by 2. Okay. So we'll get here VSO or divided by 2, and here we'll put see this L and S term is common in both actually, so that will cancel out. You will only put the value of J here, okay, which is different for the two states. So we'll put the value of J for this. J is 1 by 2. So if you put 1 by 2 here, you get actually 3 by 4, and minus when you put J equal to 3 by 2 here, so you get 3 and plus 5, 15. So you get here 15 by 4 actually. Okay. So that's what the energy difference is. Okay. And sorry, there will be H bar square also. So there will be H bar square here. Okay. So we get here VSO and H bar square divided by 2. And here you get minus 3 actually. Okay. 15 minus 3, that is 12 divided by 4 is minus 3. Okay. So answer was to be written in terms of this. Okay. So therefore your answer will be minus 3 actually. Okay. So let's go to another question. It says two particles, each of rest mass m0, move towards each other with equal speed 0.5 c. If energy of one in rest frame of another is alpha m0 c square, so you have to find the value of alpha. Okay. See, the question is something like this. There is a particle, its rest mass is m0. It is moving in this direction with the speed c by 2, 0.5 c it is. And that particle, its speed is again c by 2. Its rest mass is also m0. So now question is we have to calculate energy of one particle in rest frame of another particle. So for that we need to calculate speed of one with respect to 2, or speed of 2 with respect to 1, whatever. So let's calculate speed of 1 with respect to 2, which is written as v1 minus v2 or divided by 1 minus v1 into v2 or divided by c square. Okay, so that will be equal to c by 2, and here it is in opposite direction. So you write minus c by 2 and 1 minus c by 2. Okay, and minus c by 2 and divide by c square. So that comes out to be, sorry, it will come out to be, I think, 4 c by 5. Okay. So now energy of one in rest frame of another will be equal to m0 c square and root under 1 minus v12 square or divide by c square. Okay, so that is m0 c square and divide by root under 1 minus, and here you get 4 by 5 c, 4 by 5 whole square. Then you put v12, you get here 4 c by 5, so c will cancel out actually. Okay. So when you simplify it, you get here 5 by, I think, 5 by 3. You get here 5 by 3. Okay. 5 by 3 and m0 c square. So therefore alpha is equal to 5 by 3. That's what you get. Okay. Okay. So now let's move to another question. It says dispersion relation for 2D square lattice is omega. See, all these are actually memory based questions. Okay, so we don't have all complete details here. Okay, so I have just written down the questions. We have not written down all the options. Okay, and there might be some missing information in the question also. Okay, so here it says dispersion relation for 2D square lattice is omega proportional to k. How does the density of state depend on omega? See, this is one of the very most familiar questions in quantum mechanics or statistical mechanics or solid state physics. This is used in all these three actually units. All right. This is you very familiar. So we will be solving it using some formula. See, actually, in quantum or in solid state, we learned that if you have dispersion relation, okay, if you have dispersion relation something like this, omega proportional to k to the power s, okay, in d dimension. Suppose dimension is d, then so in that case density of state g omega depends on omega. Okay, depends on omega as omega to the power d by s minus 1. So here depend s is actually 1 and dimension is 2. So g will be proportional to omega and dimension is 2. So 2 will write here, and s, see, power here is 1 actually. Here you can see it is power is 1. So therefore minus 1. So g will be proportional to omega. That's the answer. Okay. So this will be the correct option. All right. Now, this is a very standard case. It says a Hermitian operator in cylindrical coordinates. See, this is actually the momentum operator, radial momentum operator. In some d dimension, radial momentum is actually written like this: minus iota h cross, okay, and a ddr plus d minus 1 by 2r. But in cylindrical coordinate, radial coordinate is in 2 dimensions. So we write here 2. Okay. Here we write 2. So 2 minus 1, you get 1 here. So in cylindrical coordinate, you get this answer. Okay. Now let's see this question. It says electric field at the at distance d from disk is 10% of its value at center. Electric field at distance d from a disk is 10% of its value at center. Calculate the value of d by r. Okay. See, the question is like this. See, I'm covering it quickly so that video doesn't become too long. Okay. At distance d, here electric field is supposed at center EC. Then here electric field is E is equal to 10% of EC. Okay, that's what question says. Okay, so basically E is equal to 1 by 10 of EC. That's what question says. So E is actually there is a formula. Okay, you can derive it. You assume that it has uniform charge density sigma. Okay, so if you assume that field is sigma upon 2 epsilon naught and 1 minus d upon root under d square plus z square. Okay, and that is equal to 1 by 10 and sigma upon 2 epsilon naught. That's what we have. Okay, so you just cancel these terms. Okay, you get here d and divide by root under d square plus z square is equal to 9 by 10. Okay, so now you square it and you get here 100 d square is equal to um, uh, 81 d square and plus 81 z square. Sorry, r is this is r square actually. See, I made a mistake. Here it is r square. Radius. This is radius. Okay, this is radius. R is the radius of disk. Okay, so this is r square actually. So you get here r square. Okay, so bring it to this side, you get d ultimately to be equal to 9 upon root 19 r. The r was given to be something. Okay, so you from there you can get the value of r was perhaps 25. So you get here 9 root under 19 and into 25. That's the answer. Okay, so this was one basic question. This was actually quite easy question. Level is question ka jo level hai that is of 12th class actually. Okay, now another one, average magnetic field. Average magnetic moment for spin 1 system. Okay, in magnetic field, B at temperature T is temperature T for mu B by KT much less than 1. Okay, see here mu is actually magnetic moment, we can say. Okay, so if you calculate in such case Z component of magnetic moment, it will be mu into ms actually, where ms is the Z component of spin quantum number actually. Okay, magnetic spin quantum number you can call it. Okay, so here ms is equal to plus minus 1 and 0. Okay, so that's what we have. So if in such case if you write energy, see energy, if you write energy of some state, okay, you get actually minus mu z, okay, mu z into b. So minus mu into ms or into b, that's the energy. Okay, so using this we'll put the value of ms here. So you get here minus mu b. Okay, and then you get plus mu b and you get 0 here. So there are 3 energies actually. Okay, so you get here mu b, you get here minus mu b, and you get 0 here. Okay, so if you write partition function, you get here e to the power 0 into beta plus e to the power mu b into beta. Beta is 1 by kBt plus e to the power minus mu b into beta. That's the partition function. Okay, so this I can write as 1 plus and 2. This becomes cosine hyperbolic, right? Cosine hyperbolic beta mu into b. Okay, b is magnetic field here. Okay, so that's the partition function. So now you can write here. Okay, free energy, you can write F is equal to minus kBt. Okay, ln z. That's the Helmholtz free energy, and from here you can get the average magnetic moment as mu average. This will be equal to minus See, I have written for single particle, okay, because we have to calculate average energy, so there is no need to write partition function for n particles. All right, so average energy you get here del F by del B. Okay, so that's what you get. So when you, so this is what we have. So when you put this here, okay, and when you differentiate this, you ultimately get here, see, this will become ln of this. So when you differentiate, you get this in denominator, and when cosine hyperbolic is differentiated, you get sine hyperbolic. So ultimately you get here 2, and you are differentiating with respect to b, so you get beta mu, beta outside, so beta and this kbt will cancel out, so you get here 2 mu, and here sine hyperbolic, okay, beta and mu b are divided by 1 plus 2 times cos hyperbolic and beta mu b. That's what you get. Okay, so now if there was a condition given, condition was that this beta mu b is very small. So if beta mu b is very small, you can write this cosine hyperbolic as 1, okay, and this sine hyperbolic term you can write as beta mu b itself, okay. So in that case, you get mu average to be equal to here 2, and cosine hyperbolic becomes 1, so 1 plus 2 you get 3 here, so 2 mu, and here you get mu b, and divided by, see, sine hyperbolic becomes sine hyperbolic x becomes x actually, okay. So you get beta mu b, so beta, for beta I'm writing kt here, okay. So that's what you get. So this was one option, okay. So that is the average magnetic moment, okay. Now, okay, so that's let's go to another question. It says spherical well of radius a has potential this. So for ground state, there were some MSQ questions. Okay, so let's write Schrodinger equation. Okay, so if you write Schrodinger equation here, you get something like this: minus h bar square upon 2m, and here del square operator. Okay, so you get actually, if you simplify del square operator, you get something like this: 1 by r square and d2 by, sorry, d by ddr, and here r square, and basically d radial part actually dr by dr, and plus okay, you get something like this here: l square upon 2m r square, where l is angular momentum actually, okay, and here you get r, okay, and is equal to some e and here r. You get this, okay. So this is the Schrodinger equation actually, okay. Now for ground state actually we make it 0, okay, so that we can get minimum energy. This is a positive term, okay. So for ground state, put L equal to 0. So in that case, you get here minus h bar square upon 2m, and here 1 by r square, and ddr, and r square and ddr of capital R, and here you get E naught R. So we have put L equal to 0. So here I'm writing E naught, which indicates ground state. Okay. Now we do a substitution. Okay. Put R is equal to some U by R. Okay. Now when you do that, okay, you get actually here this. This is just a basic mathematics. Okay. When you put R equal to U by R everywhere, okay, you get something like this: minus h bar square upon 2m, and here you get d2u by dr square, plus, sorry, that is equal to E naught or into U. Okay, you get this. Okay, so this equation similar to equation of particle in box actually. Okay, infinite potential well. Okay, so from here we can say that we'll get energy. Okay, यहाँ पे जो energy मिलेगा E naught will be equal to from here we can get ground state energy is equal to pi square h bar square upon 2m, and here a square. A is the radius of the spherical potential well. Okay, this is exactly similar to particle in box. Okay, this is same as particle in a box. In a box means infinite potential well actually. Okay, so that's why we can write this energy. All right, now this is the ground state energy. Otherwise for other states you get here n basically n square actually. Okay, now a ground state wave function you can write as see, when you solve this differential equation, you get the value of u actually. So u will come out to be similar to again particle box 2 by a, okay, and sine n pi. So if in place of n we are writing 1, okay, r, okay, by a. We generally write for particle box n pi x by a, or L. Width is L, then we write L here. So it will be n pi. So in place of n, we have written 1 for ground state and pi r by a. Okay. So now you, if you want to write the radial wave function, okay. Here you need to put the value of capital small u. Okay. So therefore, you get here. If you put this here, okay, you will get sine function divided by r. Okay. So which was also one option. Okay. So that is also correct. Okay, so these are the answers actually. So one option, this equation, some student told me that this equation itself was given. Okay, so obviously this is one correct option. Okay, and another correct option is this capital R is equal to sine function divided by R. That is another correct answer. And ground state energy is pi square h bar square upon 2 m square. So this is also another correct answer. So this question had actually 3 correct options. Okay. Okay, now another question. See, it says condition of Fourier transform for a function to be real or imaginary. Okay, so question was there was a Fourier transform for a function. See, question was like this: there is a function of f of x, and its Fourier transform is g of k. Now, question was, what is condition on g of k for f of x to be real? Okay, see, we know that we write f of x. See, we write f of x as some integration minus infinity to plus infinity. Okay, and here g of k and e to the power iota k, iota or minus iota, it depends on how you are defining it. Okay, and here dk. This is how we write. Okay, now if you define f star of x, you will get here minus infinity to plus infinity, and here g star of k, and here e to the power minus iota k x and dk. Okay, this we get. So now if it is real, if this function is real, we should get here f of x is equal to, okay, so this can be written. See, this here k is actually a dummy index. Okay, we can replace k by minus k. Okay, so everywhere we can replace k by minus k. Okay, so if you do that, this integration should not change actually. Okay, so in that case, what you get is, if you replace k by minus k, you get here a minus infinity to plus infinity, and here g star of minus k. Okay, and here minus k and e to the power iota kx and dk. See, actually, when you replace k by minus k, here it will become plus, here it will be minus, here there will be minus. So we and this limit will become positive, and this limit will become negative. Okay, so we'll switch the limit. Okay, so that minus sign that you get from here will get absorbed. Okay, so when you switch the limit here, there is a minus sign, minus infinity to plus infinity it is. Okay, so when you put minus, it will become plus infinity to minus infinity, but there is a minus sign here. So to absorb that minus sign, we'll switch the limit. Okay, so that's what we get. Now you see, if function is real, you should get f of x is equal to f star x. Okay, so now if you equate the two, see, f of x is this, and f star of x is equal to this. Okay, so if you equate the two, you will get here, from here you get g of k is equal to g star of minus k. Okay, this you get. Now again, if you just replace k by minus k, or you can get, okay, so something of this kind you are getting. Okay, so something of this kind, there was one option of similar type was given. Okay, all right, so now this is one thing, and if it is imaginary, you get here f of x is equal to minus of f star x. So in that case, if you equate the two, okay, see, f of x you put here, and f star of x you put from here. Okay, so you will get here, from here you will get g of k is equal to minus g star of minus k. Okay, Now, if you want to, I think if you want to relate g of k with g of minus k, you can just replace k by minus k. Okay, you will get that. Okay, so this is the question that was asked in this examination. Okay, see, I'm telling you one thing. This question, was discussed in class also in Fourier series, and this is a question directly taken from Arfken mathematical physics book. Okay, this is first and second question unsolved problem in Arfken book actually. Okay, now let's move to another question. So we are quickly covering all these questions. See, this is a differential equation, and it says it has this solution. So we have to find condition on ABC. See, this is a solution of this differential equation. So what you can do, this solution must satisfy this differential equation. So we'll put this here. Okay. So if you put this here, you get here 2c actually. Okay. When you take its second derivative, you get 2c. Okay, and minus 2x, and you put first derivative, so you get b plus 2c and x, and plus 4, and here when you put y, you get here a plus bx plus cx square, that is equal to 0. Okay, ये हमें मिल रहा है. ठीक है. Now you collect the identical type of terms. Okay, for example, x square term you collect. See, there is x square here, and x multiply, so you get x square here. So if you collect x square term, you get here coefficient minus 4c, here 2c and 2 multiply, so you get 4c, and here also 4, you get 4c. Okay, and plus when you collect x term, see, there will be x term here, so its coefficient is minus 2b, and plus here there will be x term, so it will be 4b, and collect the constant term, so you get 2c from here, and here you get plus 4a, that is equal to 0. Okay, so now let's equate coefficient of all. See, this term is actually cancelling out, so you ultimately get x into 2b here, 2b, and plus 2c, we are getting here 2c or plus 4a, so that is equal to 0. So either, okay, so we are equating coefficient of x, different powers of x from two sides. Okay, so we must have 2b equal to 0 and 2c plus 4a equal to 0. Okay, so we get b equal to 0 and c is equal to minus 2a. Okay, so these are the conditions on ABC for this to be solution of this differential equation. Okay, now move to another question. We have to find a spectroscopic terms for calcium which has this electronic configuration. Okay, see here, if you sum all here in this case, if you sum all ml, if you take sum of ml, you get here I think 1 or minus 1 you get. Okay, and if you get you sum here all ml, maximum value that you can get here is actually 2, maximum 2 you can get here. Okay, so basically we can say that here we have L equal to 1, and here we have L1 equal to 1, and here we have L2 equal to 2. Okay, so now you add these two, these are non-equivalent electrons. Okay, so you can add these two and get the total L. So total L, if you calculate, you get here L1 minus L2 to L1 plus L2. So that's the total L. So we get here L equal to L1 minus L2 1, and L1 plus L2 gives you 3. So there will be another term 2. So 1, 2, 3. So therefore in spectroscopic term we will have P, D, and F. So you will have this kind of terms. Okay. So this kind of option was actually given, which is spectroscopic term you are going to get here. Okay. Now let's move to another one. See, it says, so this was a question, this was, just taken from basic books actually. Okay, this is a basic discussion of polymatrices. Okay, question was related to actually commutation relation for polymatrices. Okay, actually, for polymatrices, there is a simple relation. Okay, it is something like this: sigma I and sigma j is equal to identity matrix and delta ij and plus iota, and here you get epsilon ijk, this is Levi-Civita tensor, and sigma k. Okay, you have something like this. All right, so this is actually relation commutation, relation for two polymatrices. Okay, now you see, if we interchange I and j, suppose we switch I and j. Okay, what happens? See, you get here psi j and psi I. Okay, so that is equal to identity matrix and delta ji you get here. Okay, and plus iota and here epsilon ji and k and sigma k. You get something like this. Okay, so I have just you can say I have written j in place of I and I in place of j. Okay, now this Kronecker delta has property. It is delta ij is equal to delta ji. Okay, but this Levi-Civita tensor has is antisymmetric with respect to exchange of any two indices. Okay, two adjacent indices actually. So this ji, see, jik can be written as minus epsilon ijk. Okay, you can write it like this. Okay, so you can put in place of jik, you can write minus here. Okay, so we'll get here, see, call it equation number 1, and here you can write sigma j sigma I is equal to this is identity matrix, and this you can write as delta ij because Kronecker delta is symmetric actually. Okay, this is symmetric tensor actually of rank 2, and this is anti-symmetric tensor, and here you get iota, and you get here epsilon ijk and sigma k. Okay, now see, if you add these two, sigma I sigma j plus sigma j plus sigma I, okay, you get here two identity matrix and delta ij, because these two terms will cancel out. This is second equation. Okay, and now if you subtract these two, sigma I sigma j minus sigma j and sigma I, okay, you get here this, see, this term and this term will cancel out and this will add up. Okay, so you get here iota, 2 iota and epsilon I j k and sigma k. So that's so this is one relation and this is another relation. Okay, so these two relations were actually asked. Okay, so you don't have to memorize all these things. Okay, you just have to keep this in mind. Okay, so this is the basic relation for polymatrices. Okay, all right, so using these actually commutation relation for spin half system is defined in quantum mechanics. Okay, so this much was only asked in examination. Okay, now this is another question. It says number of independent parameters to specify n-dimensional orthogonal matrix. Okay, so this is this can be proved in many ways. So I'm giving you an intuitive example. See, in 2 dimension, we know that rotation matrix is written as cos theta, sin theta, and minus sin theta and cos theta. This is how we write the rotation matrix. Now, this matrix is orthogonal actually. This is orthogonal. It is orthogonal matrix, and you can see it is written only in terms of one parameter theta. So therefore in 2D you can say okay, so when you are writing 2 cross 2 orthogonal matrix, okay, you are writing only you need one parameter. Okay, so when n is equal to 2, you need only one parameter. Okay, similarly in 3 dimension, you know that any rotation matrix can be written in terms of Euler angles. Okay, alpha beta gamma. Okay, so there you need 3 parameters. Okay, so basically we can say when we are writing 3 cross 3 matrix. Okay, 3 cross 3 matrix, we need actually 3 parameters. Okay, so therefore basically general formula will be n into n minus 1 by 2. Okay, because here you see when you put n equal to 2, 2 minus 1 and 2 to cancel out, so you get 1, and when you put 3 here, 3 minus 1 2 to cancel, you get 3. Okay, so therefore this will be the number of independent parameters that you need for writing or n cross n orthogonal matrices. Okay, so this was question number 18. Now move to this one. Okay, it says in an infinite symmetric potential of width 2a, state of a particle is given by this the function. Okay, so probability of finding the particle in n equal to 2 state is, okay, n equal to 2. So see, this is a symmetric potential. Okay, it says it is symmetric potential. This is minus a and plus a. Its width is 2a. Okay, width is 2a. Okay, so what we can do is here see, in this case, we know that states are written like this. Okay, you can write psi is equal to root under 2 by c, width is actually 2a. Okay, so we can write 2 by 2a, and here we write sine n pi x. Sorry, first we write cos. Okay, so cos n pi x upon 2a we write. Okay, and psi is equal to root under 2 by 2a. Okay, and sine n pi x upon 2a. This is how we write the states of eigenstates of Hamiltonian for this system. Okay, But here, you know, sorry, I wrote it twice. There is no sine term here. Okay, there is cosine only. So here in this case, you have n. Okay, here we have n is odd. Okay, and here we have n even. Okay, even integer. So this is n equal to 1 actually corresponds to ground state for this case. Okay, all right, so here you can see 2 and 2 cancel out. So basically we can write it like this: 2 and 2 we can cancel out, so we can write here 1, and so we can just move it here. Just a minute. Okay, it is something like this. Okay, here also we can cancel 2 and 2, so we can write here 1. Okay, so that's the case here. So now here if you write ground state, see the ground state, if you write, it will be 1 by root a. Okay, and here cos, we put n equal to 1 here, so cos pi x upon a. Okay, 2a, that's the ground state. Okay, if you write first excited state, we write n equal to 2. Okay, so n equal to 1 by root a, and here when you write n equal to 2, you need to use this one because this is for even. Okay, so you get here sine and pi x upon a, and when you write n equal to 3, you get here 1 by root a, and cosine, because you are using odd integer, so instead will be given by this formula. Okay, so sine 3 pi x upon 2a. That's what we have. Okay, so this is ground state, first excited and second excited state. Now you can see these terms have been used actually here. Okay, see these are the terms. So this when you multiply by root a, this becomes ground state, this becomes actually, sorry, this becomes ground state, this becomes first excited state, and this becomes second excited state. Okay, so therefore we can say that this whole wave function actually, let us write it like this. This whole thing can be written as see psi is equal to 1 by root 6, and here you can see here it is something like this. 1 by root 6 I'll keep here, and 1 by root a I'll multiply with this one. Okay, and this one and this one. Okay, so when 1 by root a multiplied with cos pi x by 2a, it gives you psi 1. Okay, so 1 by root a multiplied with this will give you psi 1, with this it will give you this, it will give you psi 2, and with this it will give you psi 3. Okay, so therefore we can write it as, here there was a factor, you can see there is factor 1 by root 2. Okay, so 1 by root 6 and sorry root 2, and here you get actually, here you get psi 2 actually here. Okay, and this gives you psi 1, so you get here psi 2, and here you get this is root 3, so this is root 3 and psi 1, and then here you get psi 2, psi 3. That's what you have. Okay, now you see these coefficients, if you square and add, you get see the coefficient here is 2 plus square, you square this coefficient, 2 plus 3 plus 1, and square of this, so that gives you 6 by 6, so that is 1. So this wave function is normalized actually. Okay, so therefore probability of being in n equal to 2 state or first excited state is just square of this coefficient. So probability of being in n equal to 2 state is just equal to root 2 or by root 6 whole square. Okay, so that is equal to 1 by 3 actually. Okay, so this is 1 by 3. So percentage wise, this will be equal to 33.33%. Okay, so percentage of probability was asked actually. Okay, so that's the answer. Okay, now this is another question. It says in 2D potential, this the wave function, and now perturbation is added. This perturbation, okay, this is the perturbation. This is added actually. This is added. So question is calculate unperturbed energy and first order shift for first excited state. So we have to calculate unperturbed energy for first excited state and first order shift also for first excited state. All right. So energy for this is a 2D potential well. So energy for this case is written as pi square h bar square upon 2m or into L square, and here you write nx square or plus ny square. Okay. Now first excited state. First excited state is written like this: nx equal to 1 or ny equal to 2, or you can write as nx equal to 2 and ny equal to 1. You can write both. Okay, so that's the first excited state. Okay, so now you see here that's so we can say that there are two states which we can call first excited state, because both of these will give same energy actually here. Okay, so we can say first excited state is twofold degenerate actually. Okay, so energy of first excited state, if you put 2 or 1 here, you get here 5 pi square. Yeah, this is the energy of first excited state. First excited state. Okay, pi. So this is 5 pi square h bar square upon 2m or into L square. That's the energy. Okay. तो ये energy of first excited state हो गया. Now if we apply this perturbation, okay, this perturbation to the first excited state, see this is a degenerate state, so you'll have to apply degenerate perturbation theory. Okay, so for that let's write the wave function for first excited state. So we can write psi1. Okay, so psi1 will be actually equal to, you know, psi for with nx equal to 1 and ny equal to 2, and let us write psi2 as psi with nx equal to 2 and ny equal to 1. So we just have to put this here. Okay, now to calculate first order correction to first excited state, we'll have to because this is degenerate state, we'll have to apply degenerate perturbation theory. For that we need to calculate matrix element of this perturbative term. Okay, so we'll have to calculate this h primed 1 element. Okay, which will be calculated like this: psi1 star and okay, h primed and psi1, okay, integrated over dx dy. All right, so we'll have to calculate like this. Okay, so this will be 1 element. Similarly, we'll calculate one. Okay, h22 element, h22. So this will be equal to psi2 star and h primed and psi2 and dx dy. And similarly we can calculate 1 2, or let me write that h primed 1 2 element will be equal to double integration psi1 star and h primed and psi2. Here you write 1 2, okay, and dx dy. Okay, now using just basic properties of integration, okay, you can check that. See, this gives you actually, see, it is something like this: x, y, and here see these two states are same actually, so you get just square of this. Okay, so you get here sine square pi x by L and sine square and pi. Here you get 2 actually, and ny you are writing 2, so 2 pi y by L and dx and dy. See, you are integrating in first quadrant actually, 0 to L, 0 to L, so nothing is negative here. Okay, all these terms are actually positive, so therefore this will be actually non-zero. Okay, so similarly so this is non-zero, this is non-zero, this will in similar logic, using similar logic, you can just say that because all this term here you will get a square of these two terms. Okay, so you will get psi2 square, and perturbation is you are integrating in first quadrant actually, so there is no negative term actually coming, so this integration will also be non-zero. And using some similar logic, you can show that these you know, off diagonal terms are actually also non-zero. Okay, so in this question, okay, this also perhaps comes out to be non-zero, you can check that. Okay, so in this question you had to show only whether these terms are zero or non-zero. Okay, you don't have to calculate it. Okay, so using some logic you can argue whether these will be zero or non-zero. Okay, so I think all these terms are non-zero. Okay, so therefore there was something written like this: a b c d minus delta. You use this equation for energy, first order correction to energy, so that was actually correct, because this a b c d, these are all non-zero terms. Okay, so this was actually correct. All right, so this is all. Okay, so in this video I have discussed 20 questions. Maybe I'll make some other video to discuss other questions, because we have not we have collected gotten some more questions. Okay, but some questions were not very clear, that's why I'm making only a solution of these many questions. And another reason is that this video also becomes too long actually. Okay, so let's stop now. Thank you very much.